Hey everyone. So this is the last test in what I'd call our four major tests that we look for to assess for convergence or divergence whenever we see a series. So just to reiterate again, the first test that we usually look to do is a test for divergence, just to see if the series diverges. Then we can say, okay, if that's inconclusive, is this thing a p-series? Is it an alternating series? Or is it a geometric series? And if it's neither of those, sometimes we can also do this other test called the ratio test. And it turns out the ratio test is really good for series that have particular characteristics. And at the end of the video, I'll discuss what some of those characteristics are. So let's go ahead and get started. So if we're given some series, basically just any series. Notice I said little n starts at big N. That just means we can start anywhere. We can start at n equals 0, n equals 1, n equals 5. It doesn't matter. Sometimes people get hung up on the starting places, and really the only series where you got to get hung up on that is the geometric series, because that's the only one that we're going to learn where it's really relevant. But anyway, if we evaluate the series of the n plus 1th term of our sequence a sub n that's in our series over the nth term, and we take the absolute value of both of those, so we just make sure those terms are positive. If we take the limit of that ratio, that's going to give us some number here, which we call rho. Oh gosh, I'm just going to warn you guys, the voice cracks they're coming in hot and heavy, so we're going to get a lot of them. Let's actually just keep count. That's one. Maybe we can take bets or something like that on how many I can do when we're getting through a video. Or it can be like an NCAA pool or something like that. Okay, anyway, so if this value rho is less than 1, then that's awesome. That means the series converges by the ratio test. If it's greater than 1, then that means the series diverges. And if it's equal to 1, that means the test is inconclusive, and basically it got us nowhere. All right, so let's look at applying this test. Oops, actually, before we do that, we need to go over some mathematical things. And the first of which is defining what a factorial is. So why are we defining this right here? Well, it's because the ratio test is great when we have series that involve factorials. So basically, anytime you see a factorial, you should always think ratio test. So for those of you that don't know, if we have something like n factorial, that's basically just a product of that number n and every number that's below it. So for example, if we have 5 factorial, that'll be 5 times 4 times 3 times 2 times 1. Another property of factorials is that 0 factorial is just equal to 1. Okay, that's number 2. We've got 2. Can we break 5 voice cracks in this video? I think we're going to get there. Okay, anyway, yeah, I had a tube shoved down my mouth in surgery. What's your excuse? All right. 3. Number 3 right there. Okay, let's keep going. So there's a couple other cool things that can happen. For example, if we have numbers like n plus 1 factorial over n factorial, that just turns out to be n plus 1, and this confuses some people when they initially see it. But what I like to say is just go ahead and write out what those two factorials are in the top. So for example, an example of n plus 1 factorial over n factorial is looking at something like 5 factorial over 4 factorial. So if we write out those factorials, we'll notice that all the terms 4 and below are going to cancel on both sides, and we're just going to end up with 5, or what that value of n plus 1 is. Now again, for example, if we do something like n factorial over n plus 2 factorial, that gives us 1 over n plus 2 plus n plus 1, or times n plus 1, and you figure that out by just writing out the factorials. So for example, if we have 5 factorial over 7 factorial, which is an analogy of n factorial over n plus 2 factorial, where in this case n is 5. Again, all of the terms that are 5 or below are going to cancel from the top and the bottom, and we're just going to left with 5 plus, all right, that's number 4. We're definitely hitting 5. Now, maybe we could go 10 in this video. I mean, that's aiming really high, but I think it's possible. Anyway, but if n is equal to 5, then n plus 1 is equal to 6, which is right there. And n plus 2 is 7, which is right there. So these two properties are ones I just wanted to illustrate to you guys, which is whenever you see factorials over each other, always think to just on a scratch sheet of paper, just write out the factorials, and you'll see where we can come up with cool simplifications to them like we have right here. So the next thing we want to go over, and this is going to be like algebra 2 type stuff, is properties of powers. So whenever we see factorials, we should always think to use the ratio test. But whenever we see things to a power of n, we should also always think the ratio test because it's really good for that sort of thing. So remember this property, x to the a over x to the b is x to the a minus b. Therefore, if we have things like a to the n plus 1 over a to the n, that just gives us a. Again, I'm just applying the rule up here to this particular function. Okay. Another way to think about this is if you had like 2 squared over 2, that would end up just being 2. Or 2 to the 5th over 2 to the 4th, that would also just be 2. All right. Now, for example, if we have something like this, a to the n over a to the n plus 2, again, just apply the formula right here, and we would get this would be a to the negative 2 or 1 over a squared. So remembering these power rules and kind of remembering how to cancel things out when you have factorials that are in quotients, these are going to help us out big time when we go to do the ratio test. So I just wanted to go over this stuff right now before we looked at some examples. So let's do that. All right, so first example, look at this series right here. Again, we see something raised to the n, and we see something factorial. So this one's just a dead ringer for using the ratio test. So go ahead and apply the ratio test to this, see what you get. All right, if you apply the ratio test, we get that a sub n is obviously n factorial over 5 to the n. So a sub n plus 1 will be n plus 1 factorial over 5 to the n plus 1. We divide that by a sub n, again, put absolute value signs on everything. In this case, neither that top or bottom is ever going to be negative. So in the next step, we just ditch the absolute value signs. And look at what we did right here. This uses the additional property that if we have something like a divided by b over number 5, we got to 5, over c divided by d. If we do this, we can just write this as one fraction as a times d, d not b, a times d over c times b. Okay? So that's what I'm just doing right here. I'm just rearranging this particular fraction. And remember, this is why I went over that stuff on that previous slide. We have a 5 to the n over 5 to the n plus 1. That just simplifies to 1/5. And n plus 1 factorial over n factorial simplifies to n plus 1. So the total limit ends up being this, which if we plug in n equals infinity, it equals infinity. So therefore, this series diverges by the ratio test because our ratio rho is infinity, which is greater than 1, so the series diverges. All right, let's look at another one. All right, try to apply the ratio test to this series right here. Pause the video. Okay, so if we do this one gets a little bit messier than the other ones, but our ratio becomes this guy right here, where again we do this sequence evaluated at n plus 1 over the sequence evaluated at n. Now in this case, we do need to keep that absolute value sign in there because we could get negative signs. But anyway, if we do this and do a little bit of rearranging, just like we did in the previous case, we end up getting this ratio. So first of all, we have a negative 10 to the n plus 1 over negative 10 to the n. That will just give us negative 10. Next, we have 4 to the 2n plus 1 over 4 to the 2n plus 3. That's just going to give us 1 over 4 squared. And then n plus 1 over n plus 2, we can't do anything about that. That just stays the way it is. So if we take the absolute value of this, that negative sign goes away from the 10. And then if we take the limit as n goes to infinity, notice we get infinity over infinity. But if we apply L'Hopital's rule, the limit of n plus 1 over n plus 2 as n goes to infinity just goes to 1. So this whole thing is just 10 over 4 squared or 10 over 16. Now 10 over 16 is less than 1. So we converge by the ratio test for this particular series. All right, so let's try one more example. Let's try this one. All right, pause the video. All right, so if you do this one, again, we want to keep our absolute value signs in this case because negative 1 to the n plus 1 and negative 1 to the n can alternate between positive and negative values. But again, we just, we add 1 to every value of n, and then we kind of rearrange everything to get it in this form. So negative 1 to the n plus 1 over negative 1 to the n just gives us negative 1. That's that negative sign right here. And then we'll have n squared plus 1 over this quantity n plus 1 squared plus 1. So if we go ahead and square n plus 1 and then add 1 to it, we end up with n squared plus 2n plus 2, and that n squared plus 1 just stays in the numerator. So if we again use L'Hopital's rule on this one, we end up getting this limit as n goes to infinity is just equal to 1. So this one is actually inconclusive by the ratio test. We have no idea whether this series converges or diverges because that ratio is equal to 1. However, if we apply the alternating series test, notice in this case, we get that our sequence a sub n in the alternating series test is 1 over n squared plus 1. And this actually meets all three of the criteria of the alternating series test. So by the alternating series test, we find that this is actually a convergent series. So this highlights, something that we got to do from time to time in series evaluations. When the series are inconclusive, we got to go to another test. And remember, I told you guys the things that we look for in the ratio test are generally things raised to a power of n, or things with factorials. Now, this did have a -1 raised to the n, so we could use the ratio test on it. However, this one to me screams a little bit more alternating series test, just because we don't have anything else raised to the power n, and we also don't have any factorials in it. But again, that's not always the case. Those are just things that you should look for when doing the ratio test. It doesn't mean that if it doesn't have a factorial or something raised to the power n, you can't use a ratio test. You can. It's just a lot of times it turns out to be inconclusive in those cases. So there we go. We've learned the major tests that we have to do in this class. The only tests we have remaining to do are some that are not so fun, which are the direct comparison test and the integral test, and we will go over those in a separate video.